Yes, next topic is efficiency of separation. Okay. Let's assume that you have many solute in a mixture, and you want to separate very nicely, which means the each chromatogram doesn't overlap with other chromatograms. Okay, so we have to consider theoretically. Okay, two factors are affecting the separation efficiency. First is the difference in elution time between peaks. Okay, that is when between peaks uh, yeah, this is rather exaggerated figure. And you have this kind of peaks, many peaks, okay, um, here and there, right? And then this one, this is illusion time, okay, the x-axis, and then those peaks must be well separated, okay. Otherwise, if they overlap, very heavily overlap, and then you don't know. Hmm, the area, actual area under this chromatogram is proportional to the solute amount, and if peaks are overlapped, and then it is difficult to separate. Yeah? And physically, it is difficult to separate. At the end of the column, sometimes you want to collect separated solute for further processing, and if the peaks are well um, overlapped, and it is not possible to get a pure sample. Okay, so the difference in illusion time is very important. The farther apart, the better separation. Okay, and second factor is that how broad the peaks are. Yeah? Although the retention or illusion time um, is uh, very close, but if the peak, yeah, this is a Gaussian peak width is very small, which means the each peak is very sharp, and it is possible to separate. Okay, so these two factors are affecting the separation efficiency. Okay, usually this is uh, the chromatographic peak. Okay, it follows the Gaussian distribution curve. Okay, and depending on the what W1 half, which is the width at half maximum. Okay, this is maximum, and half maximum here, and then the width is W1 half. Okay, if this W1 half is very small, and then the peak will be very sharp. Okay, very sharp, but still Gaussian curve. But if this one is large, and then you will get very fat Gaussian distribution curve. Okay, yeah, here, so solid moving through the column spread into Gaussian shape. Okay, this is a usual case. The longer passing time, the broader peak band, mm, which means that you have the same solute A, okay, and the solute now pass through the shorter column, and it, it passes the longer column, and then at the end of the column, the shorter column, after the shorter column, the peak in the shape is Gaussian curve, but it will be sharp. But after passing the longer column, the peak will be broadened. Okay, although the area is the same. Yeah, it's the area. This area proportional to the solute amount. Okay. Yeah. Okay, let's close. For the closer look at this Gaussian curve, and this is zero. Okay, and up to this peak, the time, that is the retention time. Okay, and it is proportional to retention volume here, VR. Okay, because we can write, we can, the x-axis may be time or volume. Okay, and let me see, and here uh, for this curve, yeah, we can calculate the this one. This is inflection point, which means if you differentiate this curve, mm, not one but two times, and then uh, there will be a zero position. Yeah? That's the inflection point. Okay, yeah, and at this position, the width of the this curve is 2 sigma, right? 2 sigma. Sigma is what? Sigma is standard deviation. Mm. But at this one, at the half maximum, this width is different from the here. Yeah? This width is 2.35 sigma, right? Better than this one, 2 sigma. It's more than 2 sigma, 2.35 sigma. Okay, and now this part, yeah, this is curved at the beginning, and then here around the maximum, it is curved. Okay, but in this part, it can be approximated by the this straight line. Okay, the straight line, and then now you what draw two straight lines here on this side and on this side, and then now it what intersect at this baseline, and then this width is uh, W equals 4 sigma. Okay, yeah, 4 sigma. Yeah, that's the property of this Gaussian uh, curve. Okay, this is the idealized Gaussian chromatogram. Okay, okay, and then height is here h, right, and width this figure in your head, in your our brain. Let's discuss, let's develop the theory, okay, for the efficiency of separation. Well, the resolution is defined by this equation. Okay, resolution is uh, the difference in retention time divided by W average. Okay, this W average maybe you know yeah, well, it is the difference in retention time proportional to the difference in retention volume divided by W average. Okay, and uh, this one it equals 0.589 multiplied by delta TR divided by W half, one half here. Okay, average. Okay, yeah, that's the resolution of chromatograms. Okay, for the quantitative analysis R must be larger than 1.5. Yeah? This is desirable. Okay, right? Otherwise, separation is not complete. Yeah, here are examples. Here are four examples. That this one, this blue line is actual chromatogram. You see, this first figure, it gives one very round shaped chromatogram, and then if you you know can run your imagination, and then you can say, oh, it is the sum of these two chromatograms. Maybe, but with this broad chromatogram, it is not. The separation is quite poor. You know, quite poor. This resolution is just 0.5. Okay, all right. But in this case, the next one, resolution is 0.75, and then you get this kind of total chromatogram. But still, these two chromatograms are heavily overlapped. Okay, and this is no good. But what about in this case, the separation is here, peak separation is 3 sigma, right? And when the peak separation is 4 sigma and resolution is 1, but still, this part is overlapped. This is no good. But when the resolution is 1.5 and then the peak separation is 6 sigma, yeah, this is good resolution. Okay, these peaks are well separated. Okay, here's an example measuring resolution. The question is a peak with a resolution returns time of 407 seconds has a width at half height of 7.6 seconds. Okay, a neighboring peak is elicited 17 seconds later with this one W1 half equals uh, 9.4 seconds. Find the solution. Yeah? Yeah, it's easy. Yeah, we use this the equation. Okay, this is constant 0.589 and delta TR is what? 17. Okay, and the first one is 407 second and next one is 17 seconds later, so delta TR is 17 second and divide by this one, the average of W1 half. The first one, let me see, half height is 7.6 seconds and second one is this one. Okay, and since it is average, so you add and divide by 2 and then it is 1.18. So resolution is no good. Okay, because it is smaller than 1.5. Okay, and now let's consider diffusion. Okay, diffusion is one of the mass transport modes. Okay, okay, let's go into, before going deep into the diffusion, let's first consider here. Okay, this is not shown in the textbook here. There are three modes of mass transport. Mass is transported, like in the chromatography, your solute, yeah, that's the mass, right? And it is transported by the mobile phase, okay, from the inlet of the column and through the column, and it comes out of the column. Okay, so mass transport, that's the mass transport. And then there are three modes of mass transport, so you must memorize these three modes. Okay, first one is diffusion. Diffusion is what? The movement of molecules along a concentration gradient. Okay, the driving force of diffusion is the concentration gradient. So molecules are moving from an area of high concentration to an area of low concentration by the random motion of molecules. Okay, so diffusion can be very strictly treated mathematically. Okay, so it is just simple the mathematics. And another mode of mass transport is migration. You will see in electrophoresis. Okay, migration is the transport of a charged species under the influence of an electric field. Okay? So uncharged species doesn't migrate. Okay, although you apply strong electric field, only charged particles are moving. Uh, why? Because positively charged are moving toward the negative the electrode. Okay, and negatively charged species are moving toward a what positive electrode. Okay, yeah, that's the migration. And there is another way for mass transport, which is convection. Convection is the transport of a species by hydrodynamic transport. Yeah, simply, the convection is to you stir the solution. Okay, you shake. Now you what? Hmm? You dissolve, the sugar in water, and then usually you shake the water, right? That's the convection. Yeah, and that action is hydrodynamic transport. Okay? That's the convection. Okay? And in your textbook demonstrates the random motion, which is also called Brownian motion. Okay, here. Hmm? This is the water, and then you put a 290 nanometer diameter fluorescent bead. Okay, very small bead, but this bead is fluorescing. Yeah, right. So you can monitor the motion of this bead. Okay, you can monitor the fluorescence. Okay, and then this one is here. It may start it from here, then it randomly moves. Why it randomly moves? Because of the it is in water. Water molecules are moving. So this one, this fluorescent bead is moving because the water is randomly moving. Yeah? So it looks like a random motion. Okay, random movement of the speed, yeah, in two-dimensional way. Okay, but if you analyze this this fluorescent bead motion, right, x and y, you can separate. Here is x-axis and y-axis, and each motion you can separate, in x and y. So in this case here, it moves toward the positive x direction, and then sometimes negative x direction, like that. And then you can get this kind of curve for x motion, and also by the same way you can analyze the y motion. Yeah, this one gives the y motion. All right, and then very amazingly, okay, you get this kind of this curve. Yeah? This is a Gaussian curve. So this observation is well fitted by Gaussian curve. Wow, amazing! All right. So this is demonstration of random motion. So diffusion. Well, of course, this is not a diffusion, right? Not a diffusion because there is no concentration gradient, but not the random motion demonstration here. And diffusion also, driving force is the concentration gradient, but the movement is done by the random motion of molecules. Okay. Yeah. So let me see. Let's go back here. Yeah. So how diffusion occurs in the chromatographic column? Yeah. This figure demonstrates quite well. Yeah, this is column, right? Long column, and you inject here. This is inlet of the column, and this is outlet of the column, right? Inlet, since you inject it, and then all the solutes are concentrated in this very narrow region. Okay, like a spike. And then now the mobile phase are moving your solute through the column, and then now this solute are moving, and at this point, right, since the solute contains uh, different solutes, and solutes are moving, are random moving back and forth, and then its distribution, it is just like a Gaussian distribution curve, and then still is moves along the column, and at this point, what, total amount is the same, but the difference is that what, the peak height becomes smaller, but it becomes fatter. Okay, that driving force is diffusion. Okay, yeah, the main cause of the band broadening is diffusion. Yeah. And here, so let's consider the unit, concentration unit, the mole per volume, right? And diffusion coefficient. Yeah, D is called the diffusion coefficient. Okay, diffusion coefficient is the measure of how fast diffusion is. Okay, the unit is area divided by second. Okay, yeah, all right. So definition of diffusion coefficient here, is defined by this equation. Yeah? The flux, the flux, you see, flux is the amount. Yeah, is expressed in mole, amount per unit area per unit second. Okay, here. This is definition of flux here. Let's look at this figure. Let's assume this kind of small, you know what the box here. And then flux, anyone now it's moving through this box, and then one flux means what? Amount per unit area and unit second. Okay, so diffusion. For the diffusion, the flux here, this is a high concentration area, and this is a low concentration area. The flux must be from this one, from high concentration area to the low concentration area. Okay, but here there is a very famous law. This is a fixed law, fixed force law. Now, flux is proportional to minus d multiplied by dc dx. Yeah? dc dx is the what? Concentration gradient. Okay, along this axis. Yeah? This axis, let's say, this is x-axis, and dc dx is what? Concentration gradient. And flux is proportional to the concentration gradient, and the proportional constant is d. D is called diffusion coefficient. Okay, diffusion coefficient. Why here there is a negative sign? Because by the diffusion, concentration gradient becomes smaller and smaller. Yeah, smaller and smaller. Yeah? That's why we put the negative sign here. And let's apply this diffusion coefficient to the chromatography, and then here we since the curve follows Gaussian distribution curve, and here we get this rather complicated equation. Okay, this is the band broadening. Yeah? Broadening of chromatography band by diffusion, only diffusion. C is the concentration. It follows this curve. Okay, this is Gaussian distribution curve. All right. Okay, very good. Infinitely sharp layer here. Infinitely sharp layer with mobile phase moles of cross-section area spreads by diffusion as travels. Okay, Gaussian profile. Yeah, this is concentration unit. T is elution time. X is distance from the center of the band. Okay. Standard deviation of band is what? This one. As is, I said, standard deviation of Gaussian curve is equals square root of 2 dt. You memorize it, this one. This is very important. And sigma is given by this equation. Square root 2, the constant, d is the diffusion coefficient, and t. If diffusion coefficient is very large, yeah, that means what? The species are moving very fast, yeah? And then sigma becomes faster, yeah? Which means that the chromatogram becomes fatter and fatter. Okay, and also if time increases and the band here the band is broadening is much higher than this one. Okay, so bandwidth is proportional to what? Square root of time. Okay, so if elution time increases by 4 times, okay, elution time increases by 4 times, diffusion broadened the band by 2 times. Okay, although you increase time 4 times, actually sigma increase by only 2 times. Okay, yeah. Yeah, this table tells the representative diffusion coefficient at the room temperature. Okay, the first column is solute and second column is solvent. Okay, water also diffuse, right? Water, yeah. Although it seems rather strange, but diffusion coefficient is 2.3 times 10 to minus 9 square meter per second. Okay, and sucrose in water, diffusion coefficient is smaller because sucrose is much larger molecule than water. And glycine, yeah, is larger, smaller than the sucrose, and diffusion coefficient is this has this value. Yeah, like that, like that, like that, and you see, usually in water, in other words, in liquid, okay, hexane here, iodine, you know, diffuses in hexane, whose diffusion coefficient is 4.0 times 10 to minus 9. You know, carbon tetrachloride also diffuse in heptane. Diffusion coefficient is this one. Yeah, okay. And here, so we can conclude that diffusion in liquid is what? Order of 10 to minus 9 square meter per second. Okay. This is a usual case. Okay. This order. But diffusion of gas in gas is much faster. Okay. Look at that. This one. You know, carbon disulfide, this is gas, and it diffuses in air, okay, at room temperature, and diffusion coefficient is order of 10 to minus 5, okay, 10,000 times larger than the liquid in liquid case, okay. And oxygen also diffuses in air at the room at 0 degree, and whose diffusion coefficient is 1.8 times 10 to minus 5, okay. Yeah, so we can conclude here diffusion in liquid is 10,000 times slower than diffusion in gases. Okay, this is a usual case. And macromolecules such as ribonucleides, yeah, this is a macromolecule, yeah, whose formal mass is what 13,700, and also serum albumin, and this is much, yeah, larger molecule whose formal mass is 66,000. Okay, and macromolecules diffuse 10 to 100 times slower than small molecules. Okay, although they are in liquid, okay, this diffusion coefficient is much smaller than other cases. Okay, why? Because of their molecular size is bigger, they're much bigger. Okay. Okay, let's stop here.